Good afternoon. Glad to see everybody here. Hopefully we can keep each other awake as this goes on. Being the first talk after lunch is always kind of exciting. But do you need more volume, Judah? I'm trying. Anyway, Ron Beard was supposed to do this talk. He called me about 3 months ago and said, wouldn't you like to do it? And I said, sure. So now we're both on the paper. One disclaimer, this goes back to the 60s. And Mark and I were just talking a minute ago. Everybody's memory gets worse as you get older up to a point. So you may hear other talks on the same topic from other people, and they may not agree with me. But this is the way I remember it, so that's the way we're going to do it. Space-qualified atomic clocks are obviously a real key thing in GPS. GPS is basically a predicted system. That is, it looks at what it's been doing, and then it tells you what it thinks it's going to do over some period of time, usually as much as 24 hours ahead. So for that to be accurate, the clock has to be predictable. And that's what all this is about. If it weren't for that, we could use some really cheap crystals and everything would work nicely. In GPS so far, we have used cesium clocks and rubidium clocks. The logic in that is fairly simple. Space people are very conservative about the hardware they put in. They want something that's got a history. When we started this whole thing out in the late 60s, early 70s, these were the things that had history and the things that were commercially available. The logic was that we would take a commercially available clock, modify it to fly it, and go from there. And that's exactly what we did in the early days. Later on, it got a little more complicated. There are obviously differences between cesium and rubidium. If you've worked with them, you know that rubidium tends to be smaller, lighter, uses less power, and generally is better in the short term than cesiums are. But rubidiums have drift. Cesium doesn't, at least very small drift compared to the rubidium. So that's the attraction of it. And of course, the other thing is, the commercial clocks that we start with are really quite different than the flight clocks that wind up in GPS satellites. As we go through the talk, we'll talk about some of the things we did early on in the program, and some of those we actually took modified commercial clocks and flew them. But as time goes on, they get more complicated. There's a big parts issue. You've got to live with radiation. You've got to live with mechanical vibration issues. You've got to be able to run it remotely, all those things. So that all counts up when you start defining the clock. Characteristics, we've talked about a lot of this already. You're worried about having accurate time and stability. It's got to live in the space environment. More important than that, it's got to live through launch, which is really a tough problem. Early on in the program, one of the things I did was shake clocks on a shaker. And I broke a lot of clocks. It's pretty easy to do. Anymore, you can pretty well get through it, but in the early days, that was very difficult. Another issue is reliability. As we talk about the early days in GPS, you'll see that reliability was a very big issue. It had to be compatible with the rest of the vehicle, which means it couldn't radiate anything, and it couldn't be susceptible to the other things in the satellite were radiating around it. And even more interesting, I think, is the way the vendors have changed over the years. The cesium vendor originally was a company called Frequency and Time Systems. They became Datum, became Symmetricom, now they're Microsemi. EG&G was our first rubidium vendor. That got bought out by PerkinElmer and is now Accelitos. So forgive me as we go through this if I kind of get the names all mixed up because they do run together. The name that applied one year didn't apply the next. Here's the programs we're talking about, the various blocks in GPS. GPS divided their series of satellites into blocks as they went to new contractors, new technologies. We'll talk a lot about Block 1 because that's the early days and that's where all this got started and where a lot of the things that affected the future of GPS all happened. Block 2 and 2A were the first real serious GPS satellites. Block 1 was really a debugging program when you get down to it. As you see some of the data, you'll understand it better. 2R and 2RM followed 2A. 2F, they couldn't get past the 2s for a long time. There were political issues apparently with having 3. Finally now we're talking about Block 3. But each time we went through this, sometimes we had a new contractor, we changed clocks. We found out the clocks that we built for the last set of satellites didn't work in the new ones. Either you couldn't buy the clock or it wasn't compatible with the vehicle. So all those things are going on. At the very beginning, NRL built 2 satellites called Navigation Technology Satellite Number 1 in TS1, Navigation Technology Satellite Number 2. These actually preceded the vehicles that Rockwell built. The first one, NTS-1, launched in '74. NTS-2 was 3 years later. NTS-1 had rubidium clocks in it. It didn't originally plan to have rubidium clocks, by the way. The primary clocks were going to be 2 high-quality crystal oscillators from Frequency Electronics. But as we got closer to the time for actually building the satellite, we found a small company in Germany called Efratom. And they built a clock that was really quite small. It was about like this. Compared to the rubidium clocks of the day, which were rack-mounted things, this was really quite a change. And the decision was made, well, let's take a try at this, see if we can modify one of these for space use. And we did. We took commercial clocks, literally. We bought 5 commercial Effertom Rubidiums. And, of course, I took one to the shaker early to see what was going to happen, and it came back rattling, so we knew we had a problem there. We knew we had to live with the commercial parts that were in the clock, and we knew we had to live with most of the design. So what we did, basically, was we glued the parts down that tended to shake and fall off. And we learned to live with most of the rest of it. Probably the biggest problem we had with that clock was the thermal coefficient. It was designed with a thermal compensation scheme that worked great in air, but it didn't work very well in vacuum, so our thermal performance wasn't too good. But again, the whole point of that experiment was an experiment to show that you could take an atomic clock and fly it in space and get reasonable results. NTS-2, we moved on to cesium. That was a bigger job, and it was something we were always planning to do, but it was further out. We went to what was in a small company called Frequency and Time Systems. They were in Danvers, Massachusetts. And they built us 5 space prototype clocks. And let's see here. That's this big black box right here. These were the Rubidiums, by the way. We'll talk about that a little bit more about why they look so funny. And the idea for that would be the basis for the space qualified clocks to follow. These were built a lot more for space than were the Rubidiums, but still they had a lot of things that we knew wouldn't last too long. So here's the Rubidium, and one of the fun things about this is there are 2 of these clocks here, and you can see them, they're mounted back to back. Right next to them is this big heavy looking thing, and that's a big piece of lead. We were very concerned about radiation hardness in those early launches, and of course we didn't have the option of going back and redesigning the circuits. We didn't have the option of buying rad hard parts, so that was our solution. Not a great solution, but actually it worked. We didn't really have any radiation problems. They were modified for remote operation, and that was about it. This is the Allen deviation of the commercial clocks prior to launch. This number here is part 10 to 12, so they were in the high to mid-13s at about 1,000 seconds or so. And this is actually some on-orbit data. This is frequency data. It kind of wandered around a fair amount, and a lot of that was our thermal compensation didn't really work right. But at least it ran, and it performed like an atomic clock, so we were very pleased with that. This is a little more data on the cesium. As I said, we bought several units, selected 2 of them for flight. Here's our flight performance pre-launch. That was right along the spec of an HP 5061, if you had one of those back then, with the standard tube. Looked about the same performance. This is some on-orbit data. Here's our pre-flight data. And in the longer term, we looked at the on-orbit data, and they matched up nicely, and that was good. That made everybody feel pretty good that we could actually launch it and not degrade the performance too much. The clock that flew in the Rockwell Block 1 satellites, more than anything else, was a clock built by the Rockwell Autonetics division. And this was, again, this Effertom Rubidium. This is a picture here, and that, back buried down in here is that same little Effertom unit, the same circuit boards. They mounted everything right. They did the parts right, went back and bought the right high reliability parts and the thermal parts, everything you needed for radiation. And they built the clock that looked like this. You may notice there's actually a crystal oscillator in here, a big standard commercial oscillator, and they found that was the best way to do for what they wanted to do. So there's their pre-flight data. Again, very good. There's their spec. They were well under the spec, and actually a little bit better than the ones we flew. They did a good job in building that up. However, this is an eye chart, and I kind of apologize for that, but not really. The idea was to give you a feel for what Block 1 GPS clocks did. So as we go down this side, these are the vehicles. There are anywhere from 3 to 4 clocks a vehicle, depending on which one you looked at. And going across this way is time, beginning in 1978. So here's Navstar 1. The first clock died in about a month. The second clock made it almost a year. The third clock made 2 months. The fourth clock, you can see there were a lot of problems. It was a wide variety of problems. It wasn't just one thing, that we always had a lamp problem, we always had a power supply problem, or whatever. All sorts of things were going wrong. And what you see here in this dark area is where the satellite was actually running on that crystal oscillator that's embedded in the clock. They had a good idea there when they used a good commercial oscillator in it, because several of them ran that way. That's what allowed GPS to do a lot of their testing in the early days, to have enough vehicles to test. Even though they didn't have atomic clocks, they had good crystals in them. We also introduced cesium in the same time frame. I hate to admit it, but that's the first cesium right there, that one little spot. It ran overnight and quit. It was a high voltage power supply. We'll talk about that a little more as we go through the rest of these clocks. But the later cesiums, whoops, button's in the wrong place. Later cesiums did fairly well, and later rubidiums did quite well. So this gets us through the first 6 or 7 years of the program. Now on to Block 2 and Block 2A. This is what the Block 2 cesium looked like. The Block 1 cesium was also built by Rockwell. It was based on the one that we did in NTS2. It looked very similar to that. Because cesium had no drift and because it was very predictable, it was designated to be the primary clock on the satellites. And that's just opposite of what happened in 2F. But they were good clocks, and for GPS at the time, they really worked very nicely. So the Rubidium was a secondary clock or used as a backup. This is the version of the Block 1 clock rebuilt for Block 2. They improved a lot of things. The reliability was much better in Block 2 than it was in Block 1. And one of the really neat things they did here is they came up with a thing called the ABTCU. What that was a thermal controller that sat under the clock and controlled the temperature. Because one of the things they never really did beat down in Block 1 was that horrible temperature coefficient. So they did it the easy way. They temperature controlled the whole clock and got rid of the problem. And that really worked nicely. The only downside to it was it used a lot of power. As I understand it, it used about as much power for the temperature controller as it did for the clock. Also in Block 2 and Block 2A, we looked at alternate sources of clocks. The reason for this was that for the most part, these clocks were being built by very small companies, people with 5, 10, 20 employees. And the concern always was that, well, the company won't be financially stable, that they'll go out of business tomorrow, or the one key engineer in the company will get run down by a bus, and then what are we going to do? So to that end, we went and looked at more sources for clocks. Frequency Electronics did a cesium for Block 2A, as did another small company called Kernco, which was really an offshoot of FTS. And the other interesting thing happened here, and we'll see this a lot more later, is Rockwell did a backup clock to their Rubidium with a company called EG&G, which is a much bigger company that you probably heard of. However, it was a small part of EG&G naturally. The ones they built for the alternate source looked pretty good, but nobody really knew how good they were because they had no way of testing them. We'll get to that in a little bit too. So, and the other thing that happened is Block 2 came along, the Rockwell Rubidiums, the alternate clocks got much better, so they didn't see the need to have a backup for that clock. So they basically discontinued that development. One of the things we learned early on is that to develop these clocks and support the development of contractors, support the Air Force, we needed to be able to do thorough testing on these clocks. One of the reasons that the EG&G clock was not recognized early on for how good it was is nobody had the capability of testing it. It went to several laboratories. NBS tested it, but they didn't have thermal vacuum chambers to test it in. They had good reference clocks, so they didn't get very good numbers. A few other people looked at it, and they had similar problems. Either they had vacuum, but they didn't have good references, or whatever. It worked that way. When it finally got to us, we were ready for it. And one of the things we did in there is we built a laboratory with thermal vacuum chambers. We had magnetic sensitivity measurements capability. We had radiation hardness testing. So a lot of that stuff went a long ways to making better testing. On the reference side, we had new multi-channel measurement systems. This is another eye chart, but all I'm trying to show here is that we had a lot of reference clocks. We had multiple measurement systems. Almost everything we did was at least on 2 measurement systems because measurement systems are and were and still are and probably always will be unreliable. But anyway, we had all the pieces. We had the references, we had UTC, we had the measurement systems, and just about everything we needed to do it. There's a couple of hydrogen masers in there now. So that allowed us to make some good measurements on that clock. The other thing that was going on back then in GPS that had an effect on the clocks was the way they ran the system. GPS originally had a master clock in Colorado Springs. Didn't last too long because they realized that making the system dependent on one clock was not really a good idea. And what they went to was a composite clock, which was a Kalman filter thing that took all the clocks in the system, assigned appropriate weighting, and made a GPS time out of that, and that was the real-time reference for GPS. That happened in several steps, but the main thing happened here, it was reported in 1991, so it happened in the late 80s, really, is when that happened. And a Kalman filter, if you're aware of it, has a lot of information in it, and it's a prediction type of system. It takes what it knows, it takes the measurements it's got, and it says, okay, here's what I think is going to happen in the next epoch, and the next epoch after that. And it's only as good as the measurement data you put in and the models that you provided for what you've got. And one of the problems that was discovered early on is all these clocks were treated as equals. Well, they weren't all equal. Some had different drift rates, some had different stabilities, particularly between the cesiums and the rubidiums. So Steve Hutzel published this in the early 90s about a way of adopting a different way of looking at the Qs for each clock, the coefficients applied for each clock. And he did 2 things. Number 1 is he gave each satellite clock its own Q, set of Qs, which wasn't true before. And also they went to a different way of adjusting the cues. One of the key parameters, particularly for the rubidiums, is knowing where the clock is going to go. I mentioned rubidium clocks drift. They always have, probably always will to some extent, although that number keeps getting smaller and smaller. So he found a way of finding a better way of adjusting for that drift. The Hadamard variance, if you're familiar with it, is a statistic for stability that takes into account drift. It got rid of the manual processing that was being done, and all in all, the system just worked a lot better after they did that. So that let them take advantage of the rubidiums, and that made a big difference in the way the system worked. The other thing that happened is when Block 2R came along, where's my time? Okay. They used a different contractor who used different frequencies within the system. They built a system called TKS, the timekeeping system. And we'll talk about that a little bit more, but it made it more adaptable to different types of clocks, and it did some things that the older satellites didn't do. To keep track of what was going on in space, NRL built up a rather involved, and again I apologize for the eye chart, but I'm mainly trying to show you it's a fairly involved system, where we kept track of all the satellites that GPS had, all the monitor stations. We got the data back through NGA. We did analysis at NRL to show what each clock was doing. That same data was fed back to the folks in Colorado Springs that helped work on the cues of the clocks. This is some typical data. This is taken quite a while back. This is back to 2000, 2001 timeframe. The plot on the left shows the Allen deviation, which is not a drift included statistic. And it shows what happens between rubidiums and cesiums. These lines are all taking straight off of the rubidiums. And the reason the Allen deviation took off is because there was drift in the data. So it's going to go away. The cesiums are on the bottom. So you can see how people kind of like cesium if they didn't know what the drift was. However, when you went to the Hadamard deviation over here, now things start looking a lot more equal. And in fact, as the rubidiums got better, they got a lot more equal than the cesiums did. As I say, this data is reported back to Colorado Springs. We did reports on anomalies in the clocks, and back in the early days, there were a lot of those. We get now to Block 2R. 2R had new clocks, new contractor. This is where the TKS system came in. And none of the Block 2 clocks, 2A clocks, were really available for 2R. So two things happened. They went to Kern Code. The company had done this alternate source for Block 2A. Very good clock that flew in the end of Block 2A. And they says, let's make a Block 2R clock. It's going to be a little bit different. The telemetry is different. The output frequency is different. And the other thing is you're such a small company that if Bob Kern gets run over by a bus, we don't want to be out in the cold. So what we want to do is we want to do a technology transfer between the systems. We want you guys at Kern Code to design this clock, to make the drawings. We're going to send it to a major aerospace contractor, and they're going to build it. The last line there tells the story. It didn't work. There are probably a number of reasons, but two of the biggest ones were that atomic clocks have a certain amount of magic in them. They don't reduce to a set of drawings. You could take the drawings for one of these commercial clocks you have out here in the vendor area, and I guarantee you probably will not be able to build one that works anywhere near as the one the vendor is showing you. There are trade secrets, there are things that they just know how to do, signals they know how to isolate, and that transition never really happened, so that clock never flew. So that left us with an alternate source rubidium. Remember the EG&G clock we talked about a few minutes ago. All of a sudden now it is not only the rubidium clock for Block 2R, it is the only clock for Block 2R. It's never flown before. The ground data is pretty good. NRL did that life test and we got some really nice data. But there was a lot of worry about that. Here's the acceptance test data. The same clock again. You can see it looks a little different than the Rockwell clock did, but it's still small, about like that. Designed specifically for space, specifically for GPS. Here's our acceptance test data, and I know again you can't see the numbers, but that's 10 to the minus 14. Remember the Rockwell clock was bottoming out right around 10 to the minus 13, so we picked up almost an order of magnitude in performance. Really a nice clock. This is the TKS system that came with Block 2R. TKS was designed to do a number of things, but one of the things it was designed to do was to simplify the clock, oddly enough. If you look at the block diagram of a typical atomic clock, you have a resonance. In the case of cesium, it's 9192 megahertz, kind of an odd frequency. And you typically, in a commercial clock, wanted 5 or 10 megahertz out of it. In GPS's case, they wanted 10.23 in the Block 1 clocks. To do that, you had to build some synthesis into the clock. That was another thing that could go wrong, and the idea here was you know, let's take a frequency where that crystal oscillator in the cesium clock and the rubidium clock runs at a submultiple of the atomic frequency. We get all the synthesis stuff. And what we'll do is we'll take care of that in TKS. They found a submultiple of both the rubidium frequency at 6.8 ... and the cesium at 9192 ... somewhere around 13.4 megahertz. So the clocks for block 2R all put out that frequency, or their best version of it. And that was used and compared to a high-quality crystal oscillator. There were two of them in the system. It was done through a phase meter, and that was the real weak link in block 2R, and it still is. If you look at the short-term stability of the block 2R vehicles, you'll see they're much noisier than they are in the 2As and the 2Fs. The reason for that is the TKS system is because the resolution of the best phase meter they could build then just wasn't good enough. I'm fine, I just sound this way. Thank you. So anyway, all that was built in. It had the capability of compensating for drift, for frequency offset, all that stuff, and that all flew on block 2R, and it could handle just about anything they threw at it. It was just a little bit noisy. So here's some data now, and two things happened here. I'll show you we'll talk about the life test. Now remember, 2R now, we've got one vendor. He's never flown before, and a lot of people in Los Angeles at the Air Force are very, very nervous about that. So one of the things they said is, let's do a life test. Well, if you're in a reliability business, you know doing a life test is really a complicated thing. It takes a lot of sample size, it takes a lot of time. So we did what they called a life test, but really it was a familiarization and a characterization type of test. We took a space-type environment. This is a thermal vacuum chamber here. There's the clock sitting in it. That's the block 2R rubidium. And we ran them for over 7 years in thermal vac at constant temperature. We tried cycling a little bit too, but mainly we ran at constant temperature. The idea was to see where are the weak spots in the clock, what's going to pop up that didn't show up in the acceptance test, what didn't the designer know about, and we'll get a good feel for what the telemetry is supposed to look like and the stability should look like. So these three Allen deviation plots over here, or traces on this curve, this is the on-orbit data through our measurement system. This is the life test data, and this is the life test data through a TKS system. So you see, at least at that point, the clock was actually quite a bit better than what the user saw on the ground, at least when you got the data back through the GPS control segment. For block 2RM, which was a modification right at the end of 2R to try to add some new capabilities in, they also had a chance to modify the rubidium units. The biggest thing they did on the rubidium units, while they looked at some of the physics stuff, was the parts. One of the reasons that you couldn't buy a block 2A clock to go in block 2R is because half the parts in it were now obsolete. Because these are high reliability parts, radiation hardened parts, they didn't make very many of them. When the demand went away, they just stopped making the part. If you change your design a little bit, you need a new part. So all that stuff led us to the point where they went back and redesigned a lot of the clock. And at the same time, several of the clock vendors were given a chance to develop some alternate technologies. In the end, none of those flew in block 2F. So block 2F, notice the contract was awarded in 1996. This is before block 2R flew and before we had a lot of their rubidium data. So their original design was 3 of the cesium clocks because after all they knew, particularly from block 2A and block 2, that the cesium clocks were really good. And 1 Perkin-Elmer rubidium clock. But as time went on, they got more data and they saw things. They said, maybe we ought to turn this around. And what they finally wound up flying was 2 of the Perkin-Elmer rubidium clocks and 1 of the Symmetricom cesiums. This is Symmetricom/Datum/FTS. Here's the rubidium. The company by now is Accelitas. It looks very much like the block 2R clock, but if you notice and you count the number of feet on it, you'll see it's just a little bit bigger. And that was because when we got to block 2F, the frequency went back to 10.23, so the 13.4 natural frequency thing didn't work anymore. Synthesizer went back in, and the 10.23 crystal oscillator to make the output showed up there as well. Also in block 2F, they had a backup clock, and that clock is still around. This is done by Frequency Electronics. It is a very similar design. It's a little bit, at that time at least, it was a little bit behind in performance, but it was coming along rapidly. They got a late start compared to what EG&G had at the time. This is some of the acceptance test data. The reason they see the curves differ, again, is this reference issue. At Perkin-Elmer, they had a hydrogen maser, one of our old ones, which wasn't too good, and it showed the clock bottoming out about like 10 parts in 10 to the 14th, like we had before. When they measured the clocks against each other, they got better results, which is kind of a standard thing you do if you've got a really good clock and you don't think you've got a really good reference. You measure it against another one just like it. So we found out how good they really were by that point, and they really were good. The life test got expanded. Here's our block 2R life test. When 2F came along, they said, gee, we learned enough in block 2R, we'd like to do it for 2F. So the test set up for the cesium and for the rubidium life test. In block 2R, we found a very interesting thing. We actually found two things. The first thing we found out right off was the thermal design didn't work the way the manufacturer expected it to. So that got fixed before launch. Also, we found there are a number of frequency steps in the clock, and we'll look at that too as we go. We're running out of time. And we'll show you a little bit of data. In 2F, we found out there were high voltage problems in the cesiums that caused trouble on orbit, but they fixed most of them before launch. And we also, in 2F, we found a lamp problem in the rubidium, which has since been worked on. There's the life test stability data. Block 3, we're continuing with Perkin-Elmer, and the frequency electronics backup clock is still in work, and I don't know exactly how much work has been done there, but it still exists. This is looking at things graphically. If we follow the rubidiums through, we got to that one. Here's the EG&G clock following all the way through to block 3. Here's the cesium clocks going along, quitting at block 2R, 2F, it never existed in there. And at the bottom we have a hydrogen maser. I'm going to take just a minute to talk about that. When I mentioned clocks before, I said, well, really, we only had two kinds to work with, cesium and rubidium. But the clock, back in the late 60s, early 70s, was a hydrogen maser. And the big problem with them for space was it was about that size. Most of them weighed 300 or 400 pounds, so it wasn't really viable for the early GPS satellites. There was a clock that flew early. The Smithsonian Astrophysical Observatory, Bob Vassaux, Marty Levine, flew the Gravity Probe A experiment, which was up and back kind of thing. They could tolerate the weight, didn't have to stay in orbit, didn't have to last very long. So that was the first maser that flew. But we got involved in some work at the laboratory and at Hughes Research Lab, and we got all the way through, built a Block 2 space-qualified compact hydrogen maser, and actually started the second generation. None of those flew on GPS. A little bit of quick stability data. This is Block 2A, 2R, 2RM, and 2F. These are the 2As up on top. When we get rid of them, you see a lot of the wildness goes away. But there's still some kind of funny stuff going on here in the long term. Let me show you where at least some of that comes from. The GPS clocks that we did life tests on, serial number 28 in particular, showed frequency steps. And in fact, early on in the thing, you can see they had a very particular rhythm to them. You could almost guess when one was going to happen, do up and down and back up again. As time went on, that changed a little bit along in here, but they stayed on. That's been true of virtually every rubidium clock GPS has had. The number of frequency steps, the size of them, the character of them has changed over the years, but all of them have had some at one level or another. And finally, that gets me to my last slide. And this is a history of all the clocks GPS has flown from Block 1 on, or Block 2A on, I'm sorry. Block 1 was the bed you saw that earlier. What you see in 2A is a lot of clocks. Every time the color changes, that was a change in the clock. So early on, we were still having a fair number of failures, but it was getting better and better as time went on. Here's Block 2R. You don't really see any changes. There's one little change right down here. But for the most part, and that really wasn't a clock failure. It was a questionable clock. They swapped it out. As we look at Block 2RM, they worked pretty much the same way. And the same is true for Block 2F. We've had one clock change in Block 2F. Actually, this one they just turned on one to see if it worked and then went to the rubidium. And this one they actually ran the cesium a while. And remember I talked about a high voltage problem? Well, that was the high voltage problem that did happen on orbit. So at that point, I think I'm pretty much out of time. Yep. So that does it for me. Thank you.